For this tech tip, we will be talking about combustion. And as you can see, combustion is everywhere. Think about all the burners that exist around the world. Think about coal combustion. Think about gas turbines in aircraft engines, for example. Think about furnaces, etc. But today I want to focus on two examples. The first one, large eddy simulation of natural gas combustion and CO pollutant emission prediction in an example from the DLR in Germany, and my colleague Nassim Ansari did this example. Another example that uses data and setup from the University of Berkeley will be about a lifted methane air jet flame in a vitiated co-flow, and thank you very much for my colleague Praveen Nakad for doing this simulation. Now on the first example, large eddy simulation of natural gas combustion and CO pollutant emission prediction. Without further ado, let's go to the first example from the DLR in Germany. It's called the Pre-Sinstra burner, and what you can see here is we're gonna take air and the fuel being methane. We're actually going to mix them, make them actually swirl as well, and we'll observe the combustion in the combustion chamber and look at CO emission prediction. Here is an overview of the geometry of the combustion chamber. And what we're seeing now is actually the inlet of air, and as you can see we have a swirler, and the air will actually swirl and be mixed directly with the fuel. Here's a little bit more detail of the swirler and the mesh on the swirler and the injection code. What you can also see is the high quality polyhedral mesh in this plane that I cut in the middle of the combustion chamber. And if we zoom in, we also see the high quality boundary layer that we put near to the wall to make sure we resolve the boundary layer of the flow correctly. And as usual, high quality surface mesh as well. Now, just a little bit of theory before we start looking at the simulation. What we'll do here is obviously not track the hundreds of pieces involved in the combustion. That would be too expensive, but we'll track two scalar of interest. We will track the fuel-air mixing ratio. Will give us information like flame speed, post-flame temperature, etc. And of course as well the flame location that we will track, and actually the flame surface, as you can see on the schematic at the bottom of the picture. Now let's see if that's done. I actually go in the species panel. I will open it. Let me put it back in the center for you to see everything. We're gonna choose partially premixed combustion. We're gonna use the C equation. That's what's gonna track our flame front. We'll use the flamelet generated manifold to generate all this information we talked about, like flame speed, flame temperature, etc. We set up our operating pressure, and what we do is actually we simply import a Chemkin mechanism from reaction design. You see the mechanism is imported, and I also import the thermodynamic properties. Then I go to boundaries. What are my boundaries? When on fuel I have full methane, and on the oxidizer side I have air. So you see that I entered the composition of air. I give the fuel temperature and oxidizer temperature. And then I will generate those flamelets. Those flamelets that will give me the information I'm looking for on post-flame temperature, flame speed, etc. Now let's generate those, and of course what I can do is check the flamelet we generated, for example temperature as a function of the mixture fraction, and what you can see here is the temperature peak when the mixture fraction is actually a stoichiometric mix, which is completely expected. Next thing I have to do is actually take those flamelets, but also include the influence of the turbulent flow, and that's why I generate a PDF table, and the PDF table will be what contains the key information we're going to use in the simulation for chemistry. Now I will not go into the detail of running a large eddy simulation computation, because you can find that in the turbulence tech tip. What I will do, however, is show you some of the results. Here you see an isosurface of velocity colored by the flame temperature. And you can see the cup shape of this isosurface. Why? Because the flow is swirling, and actually that creates a recirculation region in the middle of the combustion chamber, and that's what gives you this shape. Here is another view, isosurface of the mixture fraction, or that's basically an isosurface of the air to fuel ratio. And here you see the same characteristics. You see the shape that is a little bit like a cup, and that's because of the recirculation region present in the middle of the combustion chamber. And other way to look at it, you could take, for example, an animation of the temperature field on the mid-plane of the combustion chamber, as you can see here, typical of LES simulation, those nice simulation with a lot of structure and flame structure that you can capture. And as I told you, we were going to look at prediction of pollutant emission. So here I give you an isosurface of the CO mass fraction, CO being for carbon monoxide, which obviously is a pollutant. Now let's go to the second example, lifted methane air jet flame in a vitiated coal flow. Now the geometry of this example is more simple, and it will be a steady simulation. We are injecting fuel in a tube at the center, and we have a co-flow of air all around the fuel, and we'll simulate the combustion in this system. And what is interesting in this simulation is that we can actually simulate what we call a lifted flame, really when the flame looks like sitting in the middle of the air. And that's actually something that is not easy to do. Now, I just said it is not easy to simulate, so I know what you want to see. You want to see validation, and here is a great validation of actually looking at the temperature in the center line of ANSYS results versus experiments. And as you can see, they agree very well, and there is a really good prediction of the flame lift distance. CO emission prediction. Now, there is a lot of models available, and result can be dependent upon the grid resolution, but what's important to note here is when you use the right model and the right mesh resolution, you can have a pretty good estimate of the CO prediction. You see the experimental data with the dots, and you see our best result in blue. And don't be fooled, those results are actually extremely good, and that's actually a very good validation of the simulation.